10 minutes of my life wasted, and of yours. Okay, so from the beginning, state what is meant by a vector quantity and give one example. Well, a vector is both direction and magnitude. That is the vector quantity section of this question. And then give an example. Velocity is a nice and clear one, and it's also what we're going to be using later. Oh, I explained so much, and now I've got to go back over it. And that's the wrong one. No, that's fine. Okay. So with this question, we're going to be able to just do a simple speed is equal to distance divided by time, because it is a constant speed. It's moving around at the same speed all the time, so we're not having to worry about anything more complicated. There's no accelerations involved. So how are we going to find the distance around the track? Well, we can use 2 pi r because we're looking for the circumference of a circle. So 2 times pi times 0.60, that's the radius, divided by 20, which is the time taken. So that's going to be 0.19 meters per second. Okay, that's that one. This one has a bit more to it. So the figure shows the variation of the magnitude of the displacement of the locomotive from A with time t. Explain the graph shown in the figure. So the common mistakes with graphs are that people don't refer to the graph or refer to the diagrams that they're actually talking about. So explain the graph shown in figure 21.2. We can say that because it is the direct distance from A that we're talking about, the graph has to be symmetric about 10 seconds. Why does it have to do this? Well, we can look back at the previous figure. Which would show us that we have the circle. We've got A here, A, B, C, and D. So as it's moving around in this direction, it's moving away from A. And as it comes back round again, it's moving towards A. And because it's constant speed, it's the same rate in both directions, so it must be symmetric. Now, this second part, let's actually get some data from there. So we can say that at 10 seconds, that must be C. The reason we can say that is this idea of the symmetry. This is the crossing over point. Before this, it is moving away from A, and after this, it is moving towards A. So therefore, we can say that C is at 10 seconds. We've got 2 other fixed points. We can say that at 0 seconds, it must be at A. And at 20 seconds, it must also be at A because it is left from there and then returned to there. And now we're almost caught up with where I was before. Okay. So an object is placed on a smooth horizontal surface. 2 horizontal forces act on it. I'm going to try and find the thing I was working on before. I've just completely lost. Oh well. Okay. So if we look at this question, we're going to be splitting this into 3 parts because we're being asked to find the magnitude of the acceleration. We don't need to know the direction of the acceleration, we just need to know the magnitude. So if we think about this and sort of break the diagram down, we've got 7 newtons in that direction and 5 newtons in that direction. And we know that there is a 40-degree angle. So what we actually want to find is we want to find this. We want to find the resultant force. Now there are a couple of ways to do this, and the way I want to do it is I want to break each of these down into their components. So I want to look at the components, the horizontal and the vertical components of the resultant force. So the force resultant is made up of the force horizontal and the force vertical. Okay. So how are we going to find these? So the force horizontal, well, that is going to be 7 newtons minus 5 cos 40. Yeah. Because we're turning through the angle, so we're going to be using cos to do that. Okay, so that is going to be what the force horizontal is. And I'm going to leave this just as that for a bit of more accuracy for now. Sorry, precision would be fine. What about the force vertical? Well, that's going to be more simple. Only the 5 newtons has got a vertical component. So there's going to be 5 sine, because we're turning away from that angle. 5 sine 40 is equal to the force vertical. So how do we find the force resultant? Well, Fr is going to be equal to the square root of Fv squared plus Fh squared. It's just going to be Pythagoras theorem. So now we can pop this in. So the force resultant is equal to the square root of 5 sine 40 all squared plus 7 minus 5 cos 40 all squared. And at this point I am going to actually perform that calculation, which will get me with a resultant force of 4.51 newtons. So it's at this next stage where there's the next potential to slip up. And this is because we're about to use F is equal to ma, where the mass is in kilograms. And the reason why this is going to cause you to slip up is they have given it to you in grams. So we've got our resultant force. So our F resultant is 4.51 newtons. We're using F equals ma. So the force divided by the mass is equal to the acceleration. So 4.51 divided by, where is it? 0.320. We've converted from grams to kilograms. Is going to be equal to the acceleration, which is 14 meters per second squared. So there we have our acceleration. You could have done that all in one calculation, but it sort of gives you that safety net of being able to work through it more slowly. Right, now I need to actually find the next question because I have paper everywhere. Okay. Right, moving on. So, figure 22.1 shows a graph velocity v against time t for a skydiver falling vertically through the air. State how you can use figure 22.1 to determine the acceleration of the skydiver and describe how the acceleration varies with time. 2 marks, 2 things to do. So how you can use this to determine acceleration and then describe how the acceleration varies. Well, the first thing is nice and easy to state. Gradient equals acceleration, because acceleration is the rate of change of velocity. So if we're varying v against t, well, it's going to be the gradient. And then all you're asking is, well, what happens to the gradient over time? So the gradient is decreasing over time, therefore the acceleration is decreasing. So acceleration decreases as time increases. Nice and straightforward. Okay. Now, everyone's favourite questions, the longer questions where we're trying to describe an experiment. So, design a laboratory experiment to determine the kinetic energy of the car at one particular distance from the top of the ramp. In your description, pay particular attention to how the apparatus is used, what measurements are taken, how the data is analysed. So, we're trying to find kinetic energy. So, the first thing that I would think about is what's the equation for kinetic energy? It'll give me all the hints I need to have later on. So, Ke is equal to a half mv squared. So to be able to calculate Ke, I need to be able to measure my mass, I need to be able to measure my velocity. And then I need to do a calculation to get my kinetic energy. So each of these things need to be thought through. So the mass, nice and simple. So the mass you can measure. I'm doing this really in shorthand. You would need to write this out in more detail. So the mass determined using a mass balance. And then the velocity, this you could do in several different ways. And this is where some more of your marks come from, where of your things of how and what. So velocity, you can measure using light gates. Or you could measure using a data logger and light gate. Or you can measure using video techniques. So if you took a video of it, you would then be able to see the number of frames, and that way you could work it out. You would need to say that in here, the way you're measuring the velocity is actually you're doing a speed is equal to distance divided by time calculation in there. So you'd get 1 mark for saying that you would use light gates set up along the ramp to be able to determine the speed of the velocity of the car at any one particular point. But then you would get that 2nd mark for saying that you would determine the speed by dividing the length of the car, the distance, by the time taken for it to pass through the 2 light gates, or the time taken in the video for it to pass through a certain point. The 3rd mark is for saying that you would measure the mass using a mass balance and then calculate the kinetic energy using this equation. So just 3 marks for this, but you can sort of see how you would break that down, first by thinking about the equation, thinking about what you'd need to measure, then the apparatus you'd use, and then the various calculations you need to do to actually get a value from those calculations, from those measurements. Right. So, toy car is released from rest at the top of the ramp. 2 graphs show the variation of the gravitational potential energy and its kinetic energy with distance from the top of the ramp. The variation of the potential energy is linear, but the kinetic energy is not linear. Why is this? There's friction. This isn't a sort of a perfect environment where energy is transferred from one to the other without any losses. It's not 100% efficient. So saying, because there is friction, energy is going from GPE to thermal. And you just needed some kind of idea about that to provide that answer. Use figure 22.3 to determine the average resistive force acting on the toy car. Well, how could you do this? We've been given a distance and we've been given an energy and we're being asked for a force. Well, the work done is going to be equal to the energy transferred. So there's going to be a difference between this one and that one. And that difference is going to be the work that's been done on the car where you've got that energy transfer into friction. So the work done, or the energy, is equal to the force times the distance. So if we divide the work done by the distance it's gone over, we'll be able to work it out. So from the graph, you would need to measure the 2 points. So 0.50 minus 0.36, you would read this off the graph. That is equal to 0.14 joules. And so the force is going to be equal to that multiplied by the distance, 0.9, meaning the resistive force would be 0.16 newtons. Okay, it's another example of where actually marking things on the graph can be really helpful, because it will demonstrate to the examiner where you're getting your information from. Okay. Okay. Right. The extension of a metal wire is X when the tension of the wire is F. The table shows the results from an experiment, including the stress and strain of the values. So complete the table by determining the extension when the tension is 8 newtons. Okay. So what we're seeing is the idea that this is going to be a linear idea, because we're getting stress over strain, where we'd be measuring the Young's modulus. So it's going up by 0.4 each time. So this would be 1.6. And we can quite clearly see here that this is the graph. And so, yeah, so this is the graph. So it was a linear relationship. So it was a very valid statement to put that there. So figure 23.2 shows a graph of stress against strain for the metal. On figure 2, plot the data point corresponding to the tension of 5.9 newtons to draw the line of best fit through all the data points. So 5.9, we'd need to be plotting the stress against the strain. So we'd need to do 5.21 against 0.6. So 0.6, 2, 4, 6, 8, 10, 5.21. So we'd need to plot a point in there. And then this is the point where, because you know it's a linear relationship, you'd need to draw a straight line. And I would highly suggest using a ruler when you're doing this. I'm not going to, because I don't have one right here, and Sharpie and ruler doesn't mix particularly well. So it'll be one going through all of them and going through the origin. Use the figure to determine the Young's modulus of the metal. Well, you just need to identify the gradient, which again, I'm not going to do on here because I can't quite read the values that clearly. But you'd just be doing change in X over change in Y. No, change in Y over change in X. Right, and the Young's modulus actually ends up being 8.8 plus minus 0.1 times 10 to the 10. There we go. Okay, this is the final question that I think we will look at tonight. Next week I'll continue on with this paper to try and get it finished off. Apologies for the beginning of this live stream where you had no sound. I'll make sure to not do this in the future. So, a micrometer screw gauge used to determine the diameter of the wire had a 0 area. The diameter recorded by a student was larger than it should have been. Discuss how the actual value of the Young's modulus would differ from the value calculated. So if the diameter recorded by the student was larger than it should have been, well, we need to think about what effect that would have on the values that we actually care about with the Young's modulus. And so if the diameter is going, that means that the actual cross-sectional area is going to be smaller. So this is going to be relating to our stress. So this means that the stress values would be larger as stress is proportional, well, inversely proportional to the area. This would mean that the gradient would be larger, which would mean a higher Young's modulus. And here we can see sort of the three parts now. We're going, okay, what effect does diameter have on the overall calculation, how does that actually link in? What would that do to those values? And then finally, what would that do to the Young's modulus, which is what the question is about. Okay, I've been going for half an hour, despite the fact you've only heard 20 minutes of it. We'll continue on with question 4, etc. next week. So if you complete those questions before next week, we can then review them during that time. So the link to the paper is in the description of this one. So have a go at those questions. We will be doing the multiple choice questions next week and trying to push forward with the rest of the paper. But I thought for tonight we would stop here. If anyone has any questions about the questions I've already covered, then now would be a great time to ask them. Otherwise, that will be it. Okay, hopefully you found this helpful. Good night for now.